Good afternoon, everyone. Nice to see you. As always, I like talking to you. Had a great time this term so far. Hope you all know that. I was talking to John Shepherd yesterday, and was talking to him about my teaching and stuff because I never know what I'm teaching half the time. And um, yeah, we're just talking about 2022. And he was like, "What'd you do this year in 2022?" And I was like, did this course and C++ and stuff. And he's like, "Oh, it sounds good." And talking about next year. And then I realized that I might get stuck doing this again next year. And then I thought about how fun that sounds. And I thought about it's fun because of all of you and how fun this course is to teach and explore stuff with you. So just as a bit of a positive amidst all this COVID craziness, it's, thanks for the term so far. We still have a little bit to go. You've still obviously got an assignment and, another week of lectures and your lab and then the exam, so lots to do, but we can always smile. I hope everyone's doing well with COVID too, by the way, because everything's going crazy. All the restrictions, 5 kilometers from your house and masks outdoors. I went to take the bins out this morning, just the garbage out to the bin on the street because it's bin day. And I realized that if I do that tomorrow without a mask, technically I'm breaching health orders. And I was like, man, this is intense. So I hope everyone's doing okay, particularly those in troublesome circumstances. So thank you for that. Well, not thank you. Good luck with that, I guess. We're gonna finish off the hashing lecture. That's what today's one's about. Again, I'm sorry for the people that watch these recordings and they're trying to get through it, and then they go from hashing part 1 to hashing part 2, and I talk about COVID for 3 or 4 minutes. But we're gonna finish off the hashing stuff, and then we'll talk about tries at the end. So where we got to with hashing was that we pretty much extensively talked about hashing and everything it is and does. The one topic we glossed over, though, was how to deal with collisions, because the big issue was, okay, you have a hash that can convert maybe 1 billion items, 1 billion different strings into a key space of maybe 1,000 or 10,000 or something like that. So you're going to have overlap anytime you try and convert numbers. And we saw, because of how hashing works, that a hash function is essentially a function that does something, and then it returns I mod your key space, where 1,000 is your what you call a key space. So that's the reason you have collisions, is because you could hash things to these really big complex numbers, but everything still has to get moduloed. I don't know what the verb is, but everything has to experience a modulus per the key space size. So if the key space is 10,000 array elements, then that's as much as you can make it. If it's 1,000 elements, then we're going to have these collisions. So what we're talking about today is the part of this where we talk about hash collisions and what happens when these things collide. So the code we kind of had here, last lecture, the inserting and stuff, it kind of made an assumption that there was no collisions, in the sense that it would just insert things on top of it. So the code we started with just assumed that you have an array like this, and if you have item A up here and it hashes there, then it goes there. If you have item B and it hashes here, it comes here. And if you have item C and it hashes here, it just overrides that. That's kind of what we had before, I believe ish. It inserted it that way. Getting it out was a little bit... Getting it out, it technically does a check here to make sure that the key's equal, so I guess this one would just... Yeah, anyway, the point is that it just inserted over itself was part of the problem. So we need to find strategies to stop it inserting over itself, essentially. So we can store multiple values that all have the same initial hash key. The 3 ways we're going to talk about that are separate chaining, linear probing, and double hashing. Now, while there are 3 topics, 3 categories of how we can deal with this, separate chaining is kind of one way of doing it, linear probing is another, and then double hashing is kind of just a different way of doing linear probing. So conceptually, there's only really 2 major ways you have to get your head around things. Separate chaining, the first one, is kind of how you might naively solve the problem. So in some ways, I'm hoping it's one of the easier ones to understand, which is that, you know what? Rather than store one item per hash, let's store multiple. Let's actually use a linked list. So instead of having an array like this, where each thing is just like one item, let's do it instead where each thing here is actually a linked list. It's basically like an adjacency list that you've been dealing with a graph, right? Like that's all an adjacency list is. It's an array of linked lists. So we use the exact same structure here. You might think about it like rotated 90 degrees, but it's the exact same structure for separate chaining. So separate chaining solves collisions by allowing to have multiple items per array entry. So every array entry is a linked list, and all the items in a given linked list have the same hash value. So if you have like 6 different items that all have the same index, the same hash index, the same key, then you just stack them on top of each other in a linked list. So, that's okay. That kind of makes some sense. The implementation, you could imagine, is not the hardest thing in the world. It means that your items array is an array of pointers to linked lists that contain items, like these values, as opposed to just an array of values. And you can see here that the process we'd follow with it is that if you have initially an empty items array like this, and then you insert ABC into it, and let's say the hash of ABC is 2. I don't know why. Who knows how a hash function works? You don't care, I don't care, it doesn't really matter. So you insert it there into 2, and then you insert DEF, which has a key of 1, so you insert that there. Then you insert GHI, which has a key of 0, you insert that there. You insert JKL, has a key of 2, so now you have a collision where ABC had a key of 2 and JKL had a key of 2. So then, bam, now we have to add it to the linked list here. And then similarly, if we hash MNO, and it has a key of 1, we have to add it to the linked list that is at array index 1. So thankfully, again, this idea is really just piggybacking on top of what you already hopefully understand about linked lists and arrays and adjacency lists, which we've already done before. In terms of the implementation, the good thing about dealing with hash collisions is that when you deal with hash collisions, you're often just having slightly different representations or slightly different approaches to what you already had before. So the example here, for instance, is that with separate chaining, if you look at the code here, we've got our hash table representation, we've got our new hash table function, our get, our insert, and our delete, and you'll see that there's very limited differences between them. I've highlighted some of them here. So one of the obvious examples is that in this case, your array structure is your list's name is a pointer to a list object, or a pointer to the beginning of an array of list objects. So that's just saying that your array is a list. You have an array where each element is a list of items, which is a linked list type. So naturally, to implement something like this, you couldn't just like modify this in 4 lines of code. You'd need to also use a linked list ADT or implement your own. We've seen this before as well. The same was true for the adjacency list. Like, the adjacency list required you to not just like work with what you had, but you also had to bring on board the linked list ADT. You can see that in terms of initialization of the hash table, that we have to loop through all of the values here, and instead of initializing it to -1 or 0 or something like we might have had before, or you could have in different implementations. I think before they were still pointers, but in this case we set it to be new list. So each item in the array is the beginning of a new list. And then our hash get, hash insert, and hash delete actually make a lot of sense, and there's not a ton we need to go through with them, because when you do like a hash insert, you're essentially finding the array element that matters to you, and then you are that's the list, and then you simply insert it into that list. So if the list is empty, it's going to insert it at the start. If the list has items in it, it's going to have to iterate through that list, just like an adjacency list. And deleting has the same thing. You have to iterate through you have to iterate through the list to actually find the relevant element to delete. And then getting is the same thing. Like, you know how to search through a list. You start at the beginning and you iterate through all the elements until you find what you want. And then you can return that. So we're pretty much just totally piggybacking a linked list here, and that's how we prevent hash collisions. Does anyone want to tell me what some potential downsides of this are, or some considerations? Like if you heard someone was doing this, what's some advice you might give them, or something you might tell them to think about or worry about whilst they're using this kind of implementation? Yeah, so size. So Trent's kind of on the money here, and Trent says um, every single thing gets put in one slot. Yeah, so the worst case here, that we're about to talk about in the slides as well, but the worst case is pretty obvious. If you have like an array of 10 elements or something, or however many this is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then someone tries to insert 10 elements, what happens if like all 10 elements you insert, like A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, or whatever, Y, Z, if all of these things, they all have the same hash, which is say 2. So if they all have the same hash as 2, then what your structure ends up being is it ends up being like this. You know, where all of your elements are actually in one array index, one array key, and they're all stored inside that linked list there. So when we then have to think about time complexity of a separate chaining hash collision approach, we can look at the best case, whereby, I mean, let's firstly think, the absolute best case of this is when you have 1,000 items that you want to insert into the hash table, and you have, 1,000 array slots, and everything slots into one array slot. Perfect, right? That's the ideal case. When we look at things like these hash collisions, one way we can think about this is by looking at the average list length, which in this case we're going to say is defined as m on n. So if m is the number of items you store, and n is the number of arrays you have, the number of array items, it's the number of slots you have, then you could say that if m is 1,000 and n is 1,000, you could maybe fill them all up perfectly. However, this situation might be a case when you have, say, 10,000 items stored in just a 1,000 item array. So if you had 10,000 items stored in a 1,000 item array where m is 10,000 and n is 1,000, then ideally, literally your average list length is 10, right? Because if you have 10,000 items, 1,000 slots, the average number of the average length of a linked list is going to be 10, m on n. So the best case for hash collisions, particularly when you are storing more items than you have space for, is when all lists are the same length n. Basically, if you have those 10,000 items to put in 1,000 item spots, that every single array item has exactly 10 items in the list. The worst case that you could possibly have is the one I just described before in Paint, where you have one list that is of length m. And that means that, if you have these 10,000 items and you have 1,000 spots, the worst case is if all 10,000 items give the same hash that all collide, so therefore you build out a linked list downward. Now, this should then make some sense to you too, that the worst case is essentially therefore on, because if everything ends up in the same array slot, the difficulty of iterating through a linked list. Iterating through a linked list is an on operation. So because it's on, the worst case of searching through a hash table that uses separate chaining collision management is on, because you're going to have to worst case loop through n items. And the best case is 1. I mean, more specifically, the best case is like m on n, which is L, which isn't quite 1. Sorry. I've said this one wrong here. So ignore that for a sec. So this is specifically about the length of the list. So if you do have like a case where you say you have a structure like this, where it's like, oh, all right, I have all these items here. The worst case is what you want's down here because you have to iterate through everything. The best case is it's up here. So for going through that linked list, the worst case is n and the best case is 01 because it's right at the front. Jackie's asked a question which is like, why is the worst case here n and not m? Yeah, you're right. It is m. It's just we're referring here as like a list in a bubble. So you could replace these n's with m if you wanted. Some other notes. I think this gets a little bit like can get a bit complicated to, I guess, understand. But so I'm really tired today. So if you have a good hash and you have m is less or equal to n, i.e. your key space has more available slots than the number of things you need to store, then the ideal cost of any kind of hash table is 01. Because in theory, if your hash is good and there are no collisions, then everything should be constant to insert and look up and delete. Where separate chaining always comes into play is when m is greater than n. So obviously in reality, if you had 1,000 items and 1,000 key array, you would want to use separate chaining anyway because the odds that they all perfectly slot into free spots is like 0. So you're going to need separate chaining anyway. However, once m is greater than n, you're always going to have collisions. It's just mathematically a fact. And in that case, what we say is that the cost then is m on n over 2. I believe the reason for that is because this is assuming it's a good hash. So a good hash means it distributes things really evenly across the array. And what we found before is that the best case of a hash table using separate chaining is when all the lists are the same length. So the best case is when everything's the same length. So everything has exactly two squares. This is the perfect case for us. So a good hash will make things nice and even. So therefore we can say that the time complexity of lookup and stuff on a hash that is has more items to insert than it has space available is n on n on 2. So why is it m on n on 2? Well, we know that the length of one of these here is m on n for a good hash. So this is like for a good hash. Okay, so that makes sense. If you have 2,000 items to insert and 1,000 spots for it, the average length should be 2. A good hash should evenly distribute everything out there, theoretically, so that everything has a length of 2. So therefore, you could say your time complexity is m on n. Worst case, however, your average case is going to be m on n on 2, because in your average case, whenever you go through a linked list, you're on average going to find the middle element. You know what I mean? Like the worst case is having to go through the full length of every single list. So here the average case, while effectively m on n on 2, obviously the way we look at these things is often with worst case and often ignoring those coefficients. So similar thing here. It's like looking through a linked list is best 1, worst n, average n on 2, which ends up being on anyway. So in this case here, what we end up with at the end is that it's for a good hash, it is O m on n, and for a bad hash, it's going to be O of m, right? Because a good hash will distribute everything equally, so that you have a nice, like, everything is just length L, where L is m on n. And then this one here is a bad hash, where everything is, like, literally everything is just in one slot. And then it doesn't, like, then it's just going to be like OM on 2 or OM, you know? I'm getting questions in the chat about, so shouldn't this say O of m on shouldn't this say O of m over n instead of m over n over 2? I don't really think so, because, like, what we're trying to do here is communicate something, in terms of some things are literally log n and some things are literally a half log n. The reason we teach you big O notation and time complexity is so that when you look at this, you can be like, well, that 2 is irrelevant, right? But it's still a thing, you know, in this case. Like, we're actually saying quite clearly here that, no, it is actually half of that. that's just a way of talking about it. That's just a way of thinking about it. Like this is why we have these models. There is no final answer. Like this is making assumptions. It doesn't even make sense. Like how can you even have a good hash that perfectly distributes things? Like you can't, right? It's not possible. This is just a generalization. And I mean, just to reiterate this again, sorry to harp on about it, but whenever I do get these kinds of questions about, oh, shouldn't it be this or shouldn't it be that? It's like, big O notation is a communication tool, and your job is to communicate it, right? So in this case here, I think this makes sense because you're like, okay, well, the complexity is m on n on 2. Now, if you were trying to be theoretical about it, you just forget the on 2. You could say O of L, you could say O of L on 2. Like, they all kind of mean the same thing. We saw this with the graph stuff in week 7 when we were looking at, Lord, I don't even remember what it was, where we saw the log V, log E thing, and we kind of saw that they were like both kind of similar. So yeah, the worst case time complexity and the average case time complexity for a good hash would be O of m on n. And the worst case and average case time complexity for a bad hash would be O of m, because it's just the length of the list in that case. Now, one variable that you see throughout some of these slides is alpha here. Alpha is sometimes what we might call a load, or I guess a load factor. I'm not sure if that's what you'd call it, but that's just m on n. So generally m on n we just generalize as something like alpha, which helps again articulate for us how full is the hash table, as in like when alpha is less than 1, it's not full. When alpha equals 1, it's full for a good hash. And when alpha is greater than 1, it should be, it's guaranteed collisions. That makes sense. Any questions about separate chaining before we move on? Give you all 10-15 seconds. So is separate chaining ever used? Yes, it is. So the next two types of hash collisions we're going to talk about, they have benefits, but one of the downsides is that separate chaining is the only one we talk about that can handle a load of over 1. Because the other two types of hash collisions we're going to talk about don't actually work. Like they don't work once m is greater than n, without reallocating, which is a nightmare. So separate chaining is where you can use a static data structure to deal with cases where m is greater than n. The other two can't do that. So speaking of the other two, we have linear probing, which is the next one. Linear probing is really interesting. What it does is that it deals with collision resolution, and what we mean by that is, we get a hash for something, we try and insert it at a spot, but we find something's already there. Something like we've collided with something that's already been hashed there. So to get around that, we find the slot that we want to use, we find it's already inserted, so then we move one step to the right and we try and insert it at the next slot. Unless that's busy, then we try and insert it at the next slot. So you kind of iteratively move through array items until you find a slot that's free. And then you insert it at that slot. So, I mean, again, conceptually, sure, you insert, you take a key 22, you hash it, you put it here. You take a key 15, you hash it, you get 5, so you put it here. Or is that the wrong order? No, that's fine. So you put that there. And then here you get a K3. I'm just trying to make sense of this one. I'm not sure if I didn't include something. Okay. Might be going crazy. The point is that if you were to say take something like, k equals 30, right? And then try and insert it where the hash is 5, you'd look here and you'd see that there's a value here. So you say, I can't do that. Then you'd move one to the right. You'd see if this one is empty. If it's not, you have to move to the right until you find one and you're like, okay, that's not empty. Great. That's good. So then you insert it there. So it's really just go and try and put it in, and if you can't find it, instead of moving downward through a list, we're just going to move to the right through other kinds of array values. Now, implementation-wise, again, all these things are all very similar. The main area this differs in is in the insertion, the get, and the delete. In terms of the insertion, the reason, what you see here is that we actually have a for loop, because what this for loop's got to do now is, once you find the actual index you want to insert the hash into, like there, you don't just like insert it right there. You actually have to check if there's anything at that spot, and if there is something at that spot, then you break and you insert it. Sorry, if that spot's empty, you break and you insert it. But if there is something at that spot, then you need to increment your index by 1. So that I equals I plus 1 mod n is essentially, it's kind of like a circular linked list, or a circular queue. You're like just ticking one up at a time, and then going back to the start again. And then you can see here as well, if you find a spot that has the same key as you, then we want to swap to. Yeah, that makes sense. Yeah, so Waleed's right. If for example you had 3 items with the same hash, they would get placed to each other in an empty array. Gorb says, so this makes stacking one on top of one index much less likely. So, well, this makes it impossible, because this structure is not trying to stack anything. It's not trying to use linked lists. This is just saying, instead of like having each array item be like this like string of list items, we're just going to fill in other blank spots, right? Like it looks at your array and it's like, oh, well, I filled in 10 spots and I got 100 left and I've had a collision, so let's just go use one of those empty spots, you know? I mean, we do this all the time. Who's ever had a car spot somewhere and you like pull up and someone's sat in your car spot, so you just you park in the car spot next to it, and if that's filled up, you just park in the car spot next to it, right? Like it's the same kind of thing. You're like, damn it, my spot's taken, I'm just gonna go as close as I can to it. It's not ideal, but there we go. Hamish says, what if it fills up entirely? Let's talk about that in a bit. Oh, sorry. I see what people are asking now. So Waleed's question is, like, they have all the same hashes. How do you know if we take out the first one, second one, or the third one? The key here is that, no pun intended, you might have a key of 30, which hashes to 3. You might have a key of 15, which hashes to 4. You might have a key of 40, which hashes to 3, and you might have a key of 50, which hashes to 3. In these cases, you have 3 keys that have the same hash, so they're all going to end up trying to get put at the same spot. But they're all going to have different keys, and those keys are actually captured inside of the item. So because those keys are captured inside of the item, that's actually what this check here is for, this if equal k key, because it's kind of like, right, if I find a spot, like if I go to my hash point and I see a value there, I need to check that value is actually of the key I'm looking for. Because remember, your key space is greater than your index space or your hash space or whatever you want to call it. So there are like going to be some hash collisions, yes, but you don't have key collisions. There's no real sense of key collisions for associative containers, because it's like a set. Like if you try and insert comp 3311, the string, into a hash table, if you try and insert something with the same key, it's the same thing as far as the computer's concerned. It's like with arrays. Like array index 1 is array index 1. There is no such thing as multiple array index 1s. It's the key that actually helps you figure it out. So the second if statement in the top for loop up here is checking if we found the right spot. So what these 3 lines say is I found my hash, I found the index I'm looking for. Now I'm going to get into a loop which says is that spot empty? If it's empty, great, we found the spot. Is that spot already have a value in it that has the same key as me? Yes, great, we found the right spot. And if one of those two things aren't true, then we increment I by 1 and we apply the same thing to the element to the next dot. Because either you need an empty slot here, or you need to find something that already has your key as well. So like, see how here like a key has 15 and the hash of 15 is 5, so that's where we put this. If you tried to insert another 15, it would try and insert it here. It would see it's not empty, so it wouldn't pass the first condition, but it would see that the key at that particular spot is the same, so it would be happy with that. Yeah, that's correct, Waleed. Aurora says, but depending on the order you insert your items in, you could get a different hash table. Isn't that an issue? That's correct. Depending on the order you do insert your items in, you could get a different result. I don't think that's really an issue. It's just something we have to be aware of. Just to finish off this particular function here, hash get. So with hash get, it's a very similar principle where before to insert, we found the initial hash, and then we checked, is it empty or is it the right key? And if it's not, we kept looking. Hash get does the same thing where it's like we find the initial hash of the key, we then keep checking items one after another to see if they're empty or it's the right one, and then if we find it, we return it. So yeah, these functions work. The insert and the get are not too difficult. The delete's a little bit more complicated. So like a hash delete for a linear probing involves just a little bit more effort. The reason is because we basically need to shift things. Is the problem. I'm just looking at this again here. So the general problem is like if you have a structure like this, like that, and you, for instance, say I want to delete something like, let me just do this. Let me just do this like a little bit more myself. So what do you got here? You got 0, 1, 2, 3, 4, 5, 6, right? If you have a bunch of hashes, like let's say you say key 15 hashes to 3, key 20 hashes to 4, key 30 hashes to 3, key 40 hashes to 3, like this, right? Well, if you look at how this will go, it'll go, okay, key 15 gets inserted into 3, so I'll put the key 15 here, say. I might just put 15 in here. Great, and then key 20 goes into 4. Great, like that. And then we say key 30 goes into 3, so we get here and we think, oh, that's already taken, so I'll move one to the right, and then that's taken, so I'll move one to the right. So then we insert a 30 here, and then key 40 is taken and we move one to the right, like this, because it's all been taken at 3. So that's inserting. Inserting and getting makes sense. You start where you start and you keep going till you find the right spot, whether you find the thing you're looking for or the right spot to insert it. The hard part's deleting. What happens if I delete, say, 30 here? Right, so let's look back at the slides. Let's pretend I delete 30. Deletion is tricky because we need to ensure that there's no null in the middle of a probe path. A probe path is basically, when we say probe path, it's like, well, it's called linear probing because you find the key you want to start with, you find the index you want to start with, and then you just move like this. So that's like a probe path because you're probing linearly, like bouncing one at a time. So the point is, once we delete something, we need to rearrange some things. So in this case, let's say we're trying to delete key K. And back in our paint thing, key K was like 30. So we're trying to delete something with a key of 30. So we want to delete a key of 30. we go through all this. We find the hash of 30, which we know is 3, okay, because that's what the hash is. And then we have this little for loop here, which looks really similar to our insert, which is just a loop that basically just goes through until it finds the relevant element. So it does that. It starts from here, it goes here, and then it found the element right there. It found the 30 we're looking for. So we know where to delete from now. So we know that I is the right index. So what do? We free the value at that index. We set that value at that index to be null, and then we decrease the number of items in our hash table. That's all relatively standard. The problem is that we've kind of disrupted the order of the hash table now. So when I delete that, it's like, cool, we set it to null, so it's blank like normal, but we have to do some cleanup. And what that cleanup is that is moving to the next element, on the right, and then progressively, whilst we find every single element that's not null, we want to set it to null and then reinsert it into the hash table. So what I mean by that is that if we move 1 to the right to 40, like that, and then we look at 40 and we say, oh, I'm going to get rid of you. Done. And I'm going to reinsert you into the hash table, which means it would try and get put here, right? Because 40 has a key of 3. Can't fit, and it would end up here. So you might be thinking, like, why this whole delete thing? Why not just, like, left shift things? That makes sense, right? Like, why not just left shift everything? The problem with left shifting everything is that sometimes it might not make sense. I'll give you another example. Let's say we wanted to delete 20 here. We know that 20 has a key of, so we know that the key 20 has an index spot, a hash of 4. So we say, all right, well, I'm gonna go to my hash of 4. I found 20, great, okay. So that's that first part here. This is me trying to find the right thing to get rid of. So I found my 20 key. I will then free it. I will then set its value to null. I'll decrease the items, and then I have to do the cleanup. So I free my 20. The cleanup consists of going to the next element and the next element and the next element. I think I've actually given you the exact same example here by accident. Let me try. Sorry, I should have picked 15 instead of 20. So let's say I actually want to get rid of 15. So we find 15, we get rid of 15, great. Then when we reinsert stuff, the reason we don't just want to shift left again, because you might be tempted to think, oh, we'll just do that. We'll just shift everything 1 to the left. The reason that won't work is because when you clean up, and cleaning up consists of going to all the next elements, if you were to take 20 and shift it to the left, it would now be at the wrong spot. Because the key 20 hashes to 4. So you'll never find it again because you'll always be looking for it here. So that's why what we do is we find every element, we delete it, and then we reinsert it into the hash table like this. So we delete that, reinsert that. And then here we get the next element, we delete it, reinsert it. Where's it going to go? Well, the key of 30, the key 30 has a hash of 3, so it's going to go here. And then we take 40, and we delete that, we reinsert it. Key 40 has a hash of 3, so it's going to try and go here, try and go here, try and go here. So you can see that process of removing and reinserting actually make sure that the order is correct. So just to recap on that one again, when we delete, we don't like nulls lingering because it'll break our algorithm, because our algorithm by default here loops until it finds a null, right? So you have to rearrange things to get rid of those nulls. Like when we delete something, there's like a void, there's like a gap, we want to close that gap, except we don't shift anything, we simply remove and reinsert it. And that ensures that things are inserted into the right place, as I've kind of demonstrated there. This is another kind of more tactile example that involves linear probing here. We have an empty array, we insert AB, which has a hash of 2, we insert CD, which has a hash of 1, we insert EF, which has a hash of 0. Then we insert GH, which has a hash of 2, so we try and insert it here, but we have to move 1 to the right. Then we try and insert IJ, which has a hash of 1, so we try and insert it here, but we can't, so we keep going to the right till we can. This is what your hash table ends up with now. And then we try and delete AB, which is here, so we delete AB and then we have to reshift things, and then similarly we delete CD and we have to reshift things as well. Notice that when I delete CD, the IJ here actually jumps down, like that. Jackie says, if there are multiple hashes, how do we extract a key after it's shifted? Like, how would we find 40 in this case since it's stored in the fifth array, even though it has a hash of 3? I assume you're talking about this example here. I don't know what you mean by multiple hashes. I assume you mean there's multiple keys with the same hash, but the reason we find the 40 is because what happens is when you say, I've got a key of 40, and I want to find it, you start at its hash, which is 3, and then you move across it linearly until you find your key. And you might be thinking, what's the point of that? That doesn't make sense. Like, why? Like, we already know the key. Why are we searching for the key? That's weird. But the reason is, again, because you got to remember that for a standard kind of hash table thing, your key might be comp3311, but your value might be something like this. So what's actually happening here is that when we want to insert something like this into a hash table, we take the key, which is this, we hash it, which might give us like 1, and then we take the whole value and we store the entire value in this spot 1 here, like that. So that then when someone says, hey, can you get me the values for like comp3311? It goes, sure thing. I'm going to hash that. Okay, that gives me a 1. And then I'll start looking through here. I'll start from here. And then every time I look at a different array spot, I'm going to check if that's the right key. And if it is the right key, then it's like, great, I found your value for you. Like that. So, yes, and then last point here is just on the performance of some linear probing. I'm not going to lie, there's some of the math here I haven't derived myself, so I wouldn't be too sure off the top of my head. If we try and analyze the linear probing approach, we know a few things. We know that the cost to reach the first item is 0.1, as in, if you try and look up a key to get a value, and when you hash that, you get straight to the first element, right? Like if you try and get the key of 30, you're going to find it immediately. We know that's 0.1. So your cost to reach the first item is 0.1. The time complexity of this largely depends on how full your hash table is, because obviously the more full it is, and the more kind of elements you have to deal with, the more likely it is that a particular hash of a key is not going to be like at the exact spot, but it's actually going to be a whole bunch of linear steps to the side. So what this ends up meaning is that the cost of an unsuccessful search can be really expensive, because as it gets bigger, you end up having to search for everything. So like as you get to like something like this, if you try and look up something that has a hash of 1 and you look here, you kind of have to start searching through a lot of different elements. So just to be clear, when alpha is like 0, as in there's nothing in there, lookup's really quick because very little linear probing and hash collision's been done. Once alpha approaches 1, where the table is full, then it gets more complicated because you're going to have to start doing these linear probing steps. All of these kinds of complexities and analysis we're looking at here have they assume a reasonably uniform data and a good hash function. A lot of the complexities we deal with look at assume a good hash function. Sorry. But yes, we haven't got a complexity item listed here because this one gets a bit tough. Like it's like this is just something we haven't specified, but the main point to take away with this is not like a specific complexity best case or worst case of linear probing, more the idea that when it's half full, it's often like pretty quick to find things that are there and find things that aren't there, or like it's pretty quick to find things that are there and pretty quick to tell when things aren't there. But as you start to approach from like half full to mostly full, suddenly like the cost of missing a search is really high. So the use case that's appropriate for linear probing is when you're dealing with hash tables that you know aren't going to fill too heavily. In terms of like, if you know that you're going to have a reasonable load factor, like a load factor under 2/3 or something, then it's a pretty simple data structure that'll get you relatively high performance, right? So that's the kind of consideration there. So yeah, I mean, the questions in the chat, this can have really bad performance, yes, in cases like this, where, you know, say you have a large table that's like mostly full, your complexity starts to approach half n kind of thing. So again, don't worry too much about the math here. We're not gonna put pressure on you to recite any of this here. It's more just the general concept to take away from it is that linear probing gets really expensive as your load approaches 1, which means that it's full. The last type of hash collisions that we'll talk about before the break is double hashing, as you can see there. Double hashing is really similar to linear probing, except instead of stepping one step at a time, it actually jumps a much bigger step at a time. So think of it like linear probing, but with an improvement where we're just doing a more complicated step function. And the main reason this exists is to eliminate clusters, because that's what we saw with linear probing, was that there were whole clusters of things, which led to some poor performance. So I've highlighted a couple of key things here. With double hashing, you'll see that the logic is really similar to linear probing, where you have the for loops and the check for empty and check for the key and then the increment. It's just that instead of incrementing by 1 here, each loop, we're incrementing by another number. And that number is another hash of another hash mod. It's basically like, it's just, you gotta just think about it as another number, which we calculate when we create the hash table. So instead of incrementing by 1, imagine it could be like 100 or 60 or 90 or 95 or something like that. But more specifically, it's a particular hash of that number. So let's then take a look back and be like, how is this created? Okay, well, when I create a new hash table that uses double hashing hash collision prevention, or like collision management, I should call it, you can see there's actually a new property in a hash table now, which is our second hash mod. And our second hash mod here is something that we calculate when we create the hash table. So basically, there's some magic number. Don't have to worry too much about how it's created or anything. There's a magic number that is stored inside the hash table and is the same for all hash tables. It's the same for all items in the hash table. So it's not like a magic number per item or anything. It's like, no, your hash table has this one magic number in it that stays that magic number. Typically it's prime. I think the reason it's prime is just so it is less likely to kind of loop on itself. I'm not too across all of the details of the math here, and we don't expect you to be either. But short story, linear probing, increased by a magic number. That magic number is determined when the hash table is created to try and reduce the amount of clustering that happens. How does this make probe paths shorter? So I don't know if I would say, like, the main thing it does is it stops scenarios like this one here potentially, where well, this one's quite a small example, but what you want to avoid are, like you kind of said this before, Waleed, too, about like this has really bad performance if you end up with something of M approaching N and you delete something near the start, because you then have to kind of move through everything until you reach a null and then reinsert it. So the idea here is that it's just trying to prevent clusters from happening. So it just tries to distribute out that those next items throughout it. I mean, like one of the simplest ways you could imagine this gets you a performance benefit is that it actually just puts more nulls between everything, which means that when you do have to do things like deleting or searching, like because most searching and deleting ends once you find a null. So like a big way that you can improve the performance of this kind of linear probing double hashing thing is if you can simply not have giant clusters of keys, but instead have like more nulls distributed out. So the idea of incrementing by some kind of hash of a number is that you just spread yourself out more rather than dumping everything next to each other. When we look at the performance of this, again, I made the decision not to worry about getting into any of the math here. I mean, tons of stuff in this course could be substantially more mathematical than we make it. But the main thing to point out here is that it's very similar to linear probing in the sense that, I mean, if we go back here, you can see that, sorry that I've got a formula here written one way and then I decided to write it differently here. But the main difference here, the absolute main difference, is that your search hits are a little bit quicker, as in finding stuff is a little bit quicker, and then your search misses are a lot quicker. When we say a search miss, that means I'm looking for something, but I can't find it. And the reason these things are quicker is because as it fills up, it's ideally going to prevent clustering, because clusters slow down searches. That's the simplest kind of rule we have here. Double hashing, like linear probing, can't deal with a case where a load is greater than 1, as in it can only, like if you have a 10,000 item array, you can only deal with 10,000 values being inserted. Separate chaining is the only one that can deal with a load greater than 1 out of the things we've taught you here today. These two are just different takes on the same kind of concept of filling in empty parking spots, if you will. And yes, that's correct, Waleed. Instead of incrementing by 1 every time we find a collision, we do plus n. Well, again, I chose not to get into it too much for timing reasons, but specifically your increment is actually a hash of the key with respect to the hash you generated with the hash table representation. That's something I just encourage you to sit down for 5 minutes and stare at and think about a bit. I wouldn't get too caught up in the maths of it, but the main point with all these things, and this is true for hashes in general, is they're all deterministic. It's not a random number. And I think that's a good way to think about hashes for students, is that hashes often seem like random numbers, right? Like a naive person might be like, rather than insert everything into an array in order, let's just insert them in randomly so it looks like that. Hashes give you that like random-ish feel, but it's all deterministic, as in if you call the same hash function on the same key with the same modulus, then you'll always get the same value. So it's a little bit more complicated than just incrementing it by some magic number the whole time, because it's technically another hash on a key that is moduloed by the magic number. I'm just kind of I'm just trying to simplify that for the sake of the level of how we're approaching this topic in this course. Is like you're incrementing it by some non-one thing. It's a more complicated thing that's going to give you a bigger jump each time. How you calculate that is, in this case, a little bit non-trivial. Hashes are maps then. Correct. Hashes, so hashes, hash tables, hash maps, maps, dictionaries. I think they're the main ways I hear this data structure being referred to as. But yes, null is better distributed because we've prevented clustering here, and that's why we find this one is a little bit faster. So in summary, before we go to break on this, chaining is easy to implement and it allows loads greater than 1. I think chaining's pretty good overall. The only downside of it is that you need a linked list ADT, which is more code, potentially more overhead, blah blah, which makes me think that for there'd be some simpler use cases where that would maybe be an unnecessary overhead. Linear probing and double hashing are both quite fast if the load is small, like load is less than half. Though the deletion is complex, and double hashing does reduce those complexities a little bit. Now, one kind of elephant in the room is that, and I think this has kind of come up, is like what happens if your thing's full, particularly for linear probing or double hashing. If you have an array of size n and you have m items in it, and then you need even more, like it gets too big, it's not like you're totally screwed. You can actually just resize the array, like we do with other things, like resize the queue. You did this in lab 2 or lab 3. You have a circular queue, too many items get put into it, so you need to double its size and reinsert them. You can do the same thing with hash tables. The one thing to be wary of, though, is that you might be thinking, because hash tables aren't ordered, I can just double my queue size. I can just add more down the end here, like that. Bam, 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 bam. There's more. But the problem is, this is a big problem, if you think about how hash tables are implemented, every hash you get for a key, like a hash function takes in a key and it takes in the size of your hash table. So if you change the size of your hash table, you're going to change all of the keys, all of the hashes that your keys produce. So when you reallocate and you create a bigger hash table, like one that's twice as big, you actually need to rebuild the entire table. You need to delete everything one by one, and as you delete them, re-add them, because their hashes might be different. Same keys, same values, but the way the hash function's implemented, because you're increasing the modulo, you could get different results. So that's something to keep in mind. Yeah. Okay, well, let's wrap this one up and then take a 10-minute break. If you could leave some feedback for this, that would be great. We only have 2 more lectures to leave feedback on, so this would be great. Rip your phone out, pause the video if you're live, or if you're watching the recording, give some feedback, and yeah, sounds good. Thank you.